People are at the Fields Institute for the first time? So, okay, so a few people. So I just want to say there's normally an introductory spiel, but I just wanted to give a quick introduction because I'm sort of jumping in on the first minute or two of the talk to the Fields Institute. So the Fields Institute is sort of a collective project of 9 principal sponsoring universities in Ontario. We have a bunch of affiliate universities as well. And the Fields opened in 1992, I believe. But the history, for me, the history of the Fields goes back quite a lot longer, to about 100 years ago. So I like to kind of tell the story of the 1924 International Congress of Mathematicians. The conference had a different name at the time, and the IMU had a different name at the time, but same basic organization, same conference. And they were trying to figure out where to hold this conference. And if you know about history of the early 20th century, Europe was in chaos. And of course, the expectation was that they would have this conference somewhere in Europe, but they couldn't have it in Germany, which was in total chaos at that time with economic problems and so on. And they could hold it in France, but the French didn't want to have the Germans there. And so there's this big, concern over where are we going to hold this conference. And there's a lot of back and forth. They talked briefly about having it in the States, but there was somebody on the committee who had a different suggestion. That was John Charles Fields, who was a faculty member here at the U of T. And he said, okay, let's have it in Toronto, which was probably a bit of a surprising suggestion at the time. And you probably also know Fields' name from the Fields Medal, which he later endowed to honor excellence in mathematics. And so those two things are sort of the inspiration for the Fields Institute. On the one hand, fostering excellence in research in the mathematical sciences, but also providing an inclusive environment in which people can sort of do that research. And that's the story. The Fields was adamant that everyone be included. I think in the end, the actual historical truth is that the French won out and the Germans were not invited to the conference. But anyway, we stick with the spirit of Fields, which was that everyone should have been included. So as I said, I'm the deputy director. I'm up in Office 320. If you have any questions or concerns during the workshop or at any other time, you can always come up and say hi to me. And if you're here for the whole thematic program, definitely come by and say hi at some point so we can get to know each other. I also, at this point, often thank our sponsors, and we have funding from NSERC and NSF in the province of Ontario, and we're very grateful for all of that. But I would actually rather thank the organizers of the event, because these things don't happen without people actually organizing them. And so I'd like to thank Leo and the other 2 organizers of this workshop and all the organizers of the thematic program for putting together what looks like a great event. And so I'll now pass the microphone over to Leo, who will introduce the first speaker.
Thanks so much. Thanks so much, Patrick, for the kind introduction. I'm very, very excited for this whole semester. There's going to be a sporadic burst of events throughout the semester. The first one being this winter school. There's another winter school next week in general relativity. So if you're registered for that and are staying, I'm really excited for you to learn a lot of interesting things. So it's my pleasure to introduce Dr. Cole Graham from the University of Wisconsin-Madison, who's going to tell us about inviscid limits in hyperbolic conservation laws. Yep.
Okay. How's this doing? Volume was. Okay. Well, thank you very much. It's so nice to be here. Such a privilege to get to come together and think about some math for a week in a warm week in Toronto. And a special thanks, of course, to all the organizers for this semester and to Leo in particular for bringing this week together. So my general subject will be the compressible Euler equations from fluid mechanics. And I'll be interested in how these equations spontaneously develop singularities and what the role of additional viscous forces coming from friction might be in affecting the development of those singularities. And so today I want to focus on the inviscid part of the problem. So thinking about the Euler equations rather than the Navier-Stokes equations, and again, understanding how singularities, shocks in particular, come to form from smooth data in such an equation. And so the Euler equations are one of the oldest PDEs to be written down by Euler, of course, and they come out of the very fundamental principles of classical mechanics. They arise from various conservation laws. So many things are conserved. In Newtonian mechanics, we have a conservation of mass, a conservation of momentum, conservation of energy, among other things. And these three give rise to the equations that govern the evolution of a compressible fluid. So let me write one version of the Euler equations for us. And I'll express this as an evolution equation for a vector of quantities. And for simplicity, I'm going to work in one dimension here. So I'm thinking about a compressible gas on the line, let's say, which of course we could also envision as a three-dimensional body of gas that happens to be symmetric in two of the axes, and so is only being perturbed in, say, the x direction. So I want to track various fundamental properties of this gas as they evolve in time. And the first I'll be thinking about will be the mass density of the gas, the mass per unit volume. I'll call that rho. And the next will be a bit more curious of an object, the momentum density of the gas, which has a more familiar expression that I'll write in a moment. But that, again, just tells you about the amount of momentum contained in a given unit volume. And then finally, the energy density. And so I'll write these expressions first and then offer a little bit of interpretation. So the time evolution of this vector of quantities, three scalar quantities in this case, because we're in one dimension, so the momentum is just a single scalar number, are related to the spatial derivative of certain functions of these quantities. So I'll have m here, I'll have u times m plus the pressure. And I'll offer a bit of interpretation in a moment, but briefly, u is the velocity of our fluid, and p, as I mentioned, is the pressure of the fluid. And down here, we'll have the velocity times the energy density plus the pressure. And it turns out that this collection of derivatives is equal to 0. So where is this coming from? Let me think about the first equation here. So the equation for the mass density of the gas. So this equation is expressing the conservation of mass overall. And I could think of that in a very simple way. By the way, where should I stop on this board? Is here visible? In particular, maybe Leo is the little higher.
That's good.
Below is not so good. Yeah, so I'll mark that off here. So in fact, I'll just switch over to another board here. So let me think about where this first equation might come from. And I'll write out the momentum density in a more familiar form as the velocity times the mass density. So here we have momentum density, mass density, and velocity. And in that form, this first equation is the well-known continuity equation. And the idea is that if I'm studying the evolution of the gas and I'm looking at a small interval between two locations, x and x plus dx, let's say, and I want to think about the total amount of mass contained in this small interval as it evolves in time, then the time rate of change of the amount of mass here could only be caused by an influx of material from the left and an outflux of material on the right. And so the incoming flux here on the left, the amount of mass being dragged into this little region of study would be given by the velocity at that location times the mass density. That would be the rate at which new mass is being pushed into this region. So that would be U rho evaluated at that left endpoint, x, and the flux on the right will be very similar, the same quantity evaluated at the slightly shifted location, with the caveat that material flowing out on the right will decrease the amount of mass in our little region of interest. So this will come with a negative sign. And given that, we could say that the rate of change of mass in this small interval should, on the one hand, just be given by the time rate of change of the mass density there times the length of the interval. And on the other, that should be given by the difference between these quantities in an infinitesimal sense. So here we'll have U rho evaluated at, let's see, maybe I'll put it like this, x and x plus dx. And if I divide by dx and take some limits, I'll find this equation in the limit, that continuity equation. Now that's the simplest of the evolution equations I've written up here. And I'll point out that some of the subsequent equations have some similarities with it. So we have an m here, and we have u times m. So this term looks exactly like the continuity equation, just with a different variable. And likewise, we have E and U times E, but then there are some additional terms that come from other opportunities to change the momentum and energy densities beyond simple transport. And I won't walk through the derivation of those other equations in full, but let me just say that this second equation, for example, can be viewed as an application of the second law, Newton's second law. Because the time rate of change of a momentum can be related to a force, and or excuse me, I should say it should be related to an acceleration, and Newton's second law would relate that acceleration to a force. What are the forces acting on a gas? In this case, I'm thinking of a gas that is moving horizontally, let's say, and is not experiencing any pressure, or excuse me, any gravity gradient, but there are internal pressures that develop in this gas. Different regions of the gas can experience different pressures, and if I have a high pressure here and a low pressure here, that will accelerate the gas from one location to another. And so that pressure will enter as a force term in Newton's second law and give you this additional term here. And similar considerations can be expressed for the conservation of energy. I won't go through the full derivation. So this is a somewhat elaborate collection of first order PDEs. And as I've written it here, it doesn't appear to be a closed set of PDEs. There's more letters on the board than there are evolution equations. But we can express some of these additional letters in terms of the three state variables, rho, m, and e. So, for example, the velocity, u, is explicitly given as the ratio of m and rho. So, in fact, wherever I see a velocity here, I can mentally replace it by a function of m and rho. And that gives me one step closer to thinking of this as a closed collection of equations. But there's still this pressure term here. I don't explicitly have an evolution equation for the pressure. But again, using an equation of state one can derive an expression for the pressure in terms of these state variables. So in terms of rho, m, and e. So this is some sometimes complicated expression of these variables. The exact form of this function depends on the gas you happen to be studying. It depends on the internal structure of the molecules of that gas. And I won't kind of delve more deeply into that structure, but one can express the pressure just directly as functions of m, rho, and e. And so as a consequence, everything in this vector is actually some function of the state variables that I've studied, that I've listed out here. So I can view this as an example of a system of conservation laws where I have a time rate of change for a vector of quantities, and that's related to a spatial derivative of some nonlinear function of those quantities. So as a consequence of this, I could interpret this vector as satisfying a nonlinear conservation law of this form. And again, this function f, the so-called flux of this vector, is an expression for all the kind of implicit dependence of all these expressions on the state variables, rho, m, and e. And so one perspective I want to develop here is that the study of the compressible Euler equations can be, in many ways, subsumed into a broader study of nonlinear conservation laws of this form. And sort of the important point is to extract a few key features of the Euler equation, some nice properties, let's say, that allow us to say some particularly nice things about the solutions of this equation. So I won't really be relying heavily on this special representation of the Euler equations. I'll sort of abstract it and think more broadly about that collection of conservation laws, just bearing in mind that occasionally we'll want to return to these equations to extract one useful property or another. Now there's another way of writing this out. So if I apply the chain rule to this nonlinear function of my state variables, then I could equivalently write this in this form, where A is now a matrix that represents the derivative of the flux function. And this matrix depends nonlinearly on your state variable, which is a vector, and then it goes and multiplies the vectorial quantity here, the spatial derivative of our state variable, which then feeds into the rest of the equation. So here, A is a matrix given by the derivative of your flux function f with respect to the various entries of your state variable psi. And it's really this form that I want to focus on. I want to understand how do the properties of this matrix valued function affect the development of solutions to this equation. So let me pause and see if there are any questions. Okay. So let's suppose for a moment that this matrix A is constant. Meaning it's not nonlinear, it's actually independent of the function psi. So then we have a linear evolution equation, and if I diagonalize that matrix A, then I could actually decouple this system of equations into a collection of scalar equations, each of which is linear. So if we diagonalize, we would end up with, as I mentioned, a collection of scalar equations for the different eigencomponents of psi. And then the action of A would just transform into scalar multiplication by an eigenvalue. And for each eigencomponent, this is just a linear transport equation. So this is a super simple thing. Solutions of this are just getting dragged along the real line at the constant speed lambda. So this is linear transport at speed lambda I. Now, of course, this is a gross caricature of the actual nonlinear system of equations we have, but my point is that the eigenvalues of A are probably going to play a major role in the analysis, and we should think of those eigenvalues conceptually as speeds that should represent something about how different disturbances in the gas spread and propagate. So although this simplistic analysis does not carry over to the nonlinear model, this kind of underlying idea that eigenvalues could be thought of as speeds that are transporting certain characteristics of the gas, that has a lot of value to it. So returning to the more complex nonlinear system, I'd like to ask, can I identify these eigenvalues? And do they have some physical significance? So what are these eigenvalues representing various speeds? And again, this is something that I will not go through a full derivation of, but I want to appeal to some fairly well-known facts about gas dynamics. So if, for example, if we linearize the equations about a state psi, it's well known that one can extract a wave equation from the linearization of these compressible dynamics. And this makes sense. That wave equation should be what describes the propagation of sound in a room, for example. And that sound is propagating at a certain speed, which has been well understood for centuries as an expression of the state variables. So if we linearize around a state, one can derive a wave equation with a certain speed that I'll call c. And this speed can be expressed in terms of the physical properties of the gas as the square root of the partial derivative of that pressure function with respect to the mass density. So for a given gas, I have a pressure function of this form. I could differentiate it in the first coordinate. I'll get some other nonlinear function, and its square root will give me the speed of sound in this gas linearized around the particular state psi. So implicitly, this partial derivative is a function of the state variables, and I'm evaluating it at psi here. So that gives us a hint that the speed of sound should be related to the eigenvalues. And of course, sound in one dimension can propagate both in the positive and negative directions. So there should be two sound speeds, one going left, one going right. And finally, we need to remember that this sound is propagating through a medium that is itself moving. we're in a gas that's sliding around on the real axis. It has intrinsic velocity u, and the sound is propagating with respect to that moving velocity of the gas. So to put it another way, sound is propagating, but in a moving reference frame that is traveling at speed u. So in an absolute fixed reference frame, in the kind of Eulerian coordinates that I'm studying here, sound propagation is going to occur with speed u plus or minus c. So those respect left and right moving sound in the co-moving frame of the gas. So those are going to be two eigenvalues. Of this matrix A, again, in the specific case of Euler. Now, the Euler system that I've written down has three components to it. So A is a 3 by 3 matrix. There should be a third eigenvalue. And turns out that third eigenvalue is just the velocity itself, u. So the third, which is not detected by this wave derivation, is just u itself. There's some sense to that. U, of course, is a velocity already. So maybe it's no surprise that that velocity is itself one of the eigenvalues of this matrix A. This represents the simple transport of the entropy density within the gas. So this is another physical quantity that one can track. And the entropy does not move with sound waves. It actually just gets dragged around by the velocity of the gas itself. So that would kind of give you the corresponding eigenvector here. So that explains why we find this additional value of u. All of this can, of course, be derived by writing down an explicit form for A. That's pretty painful in the coordinate system that I've chosen. There are other choices of state variables that one can make that make it a bit more transparent that these should be the eigenvalues of that matrix. But it's not something that I want to dwell on over much. I just wanted to convey that there's some reason behind the values of these eigenvalues, and these expressions are going to play a major role in the analysis of the gas dynamics. And one very important fact here is that for physical gases that are not at vacuum, meaning rho is strictly positive, and we'll always be working away from vacuum, the sound speed is going to be strictly positive as well. Okay, and of course this is our intuitive experience in real life. Sound doesn't end up just building up around my mouth without propagating. So the consequence of this is that these three eigenvalues are all separate from one another, and they can never collide or overlap. So we're in kind of a particularly nice scenario, say from a spectral theory perspective, where we have a collection of eigenvalues and there's never any degeneracy. They're all simple, and again, they can never collide. And that tends to lead to various nice analytic properties. So that would imply that the eigenvalues here are going to be analytically as regular as the matrix A itself. And the matrix A, for a typical gas, would be a smooth function of the state variables. So now that'll tell us that these eigenvalues are smooth functions of the states. And in addition, their corresponding eigenspaces, say their normalized eigenvectors, are also going to be smooth functions of the state because they can never cross. If you had the presence of some degeneracy where eigenvalues collide, then the eigenspaces can depend in a more complicated and irregular way on the state variables. But that issue does not occur here, and that's a particularly nice aspect of the theory. So this is one of those kind of nice properties that comes from the Euler equations, which is not generally true for a completely arbitrary nonlinear equation of this form. And this nice property has a name. It gets used all the time. It's what makes this a strictly hyperbolic system of conservation laws. So distinct eigenvalues has an associated name so this system of conservation laws is referred to as being strictly hyperbolic when you're in this case. And as I mentioned, it has among many other things, it has the nice consequence that these various expressions vary smoothly in the state variables. Okay, so that's most of what I wanted to share regarding the equations themselves. Now I want to think about the potential for singularity formation in these equations. So how is it that we could start with smooth conditions and spontaneously develop something irregular out of this evolution? And the story is very familiar in the scalar case. So I just want to briefly recall how singularities can form in the setting of a scalar conservation law. So if I have some scalar function, theta, satisfying a scalar conservation law of this form, where now A, being a scalar, can be interpreted as the single eigenvalue of the advection matrix in this case. So A is playing the role of lambda on these boards. How can such a thing spontaneously develop a singularity? Well, we could solve this equation using the method of characteristics. And along a characteristic, which would be a path moving at speed a of theta, theta would be conserved. That's what this equation is telling us, which if theta is conserved or constant along the characteristic, then the slope of the characteristic, the speed, will also be conserved because it's just a function of theta. And therefore, you're moving at a constant speed. So the characteristics of this equation are constant slope lines in space-time. So the solution is constant along paths of, let me say, speed a of theta naught being the initial condition. And in principle, there's nothing that would prevent several different paths of this form from intersecting at some future time in space-time. So we would start off from some smooth distribution of theta naught, but we could potentially have characteristics that converge on one another and begin to cross. When they cross, they're trying to drag different values of theta to the same location, so you have some discontinuity developing. And that would be represented by the formation of a shock in this scalar conservation law. So these collisions are equivalent to shock formation. And I want to highlight that the way you would get a collision would be, it's kind of a silly thing to point out, but in order to develop a collision, we need these characteristics to potentially move at different speeds. If all the characteristics are parallel to one another, then they'll just shift our initial profile at a constant speed forever, and of course there will never be any crossing. So it's crucial to develop such a structure that we have variable speeds, and in the context of a scalar law, that's a very simple condition. This is all tied to A prime being not equal to 0. In other words, to say that A is not constant. And that condition is known as genuine nonlinearity. So again, it has a nice name because it plays an essential role in the theory. We say that a law is genuinely nonlinear at some value theta if this condition holds there. And the name sort of speaks for itself. It's telling you that this isn't a linear equation masquerading as a nonlinear one. When you're at a value that is genuinely nonlinear, you have the potential for singularities to develop, and you will behave fundamentally differently than the linear equation there. So I'd like to kind of transfer this basic idea to the setting of a more elaborate problem where I have a system of conservation laws. And just to be clear, when I say I have a system of conservation laws, I mean that I'm thinking about a vector valued quantity with several scalar equations in parallel rather than just one. So it turns out one can identify scalar equations hiding inside more complicated vectorial systems. And the way to see this would be the following. So let's fix an eigenvalue, lambda, which is a function of psi. So we're just choosing one of the eigenvalues of our problem. For the moment, I'm working in a general system. So this is some nth order system. Doesn't necessarily have to be Euler. Fix an eigenvalue of a hyperbolic conservation law, meaning the eigenvalues are all distinct. So we have some nice isolated simple eigenvalue varying smoothly, and it has an associated right eigenvector. R of psi, so that A of R is equal to lambda R. And if my state variable has n components to it, this is living in Rn, and then the right eigenvector itself is also living in Rn. In fact, if I've normalized it, it's living on the sphere there, but that's not terribly important. The point is just that this is a map from Rn to itself. So I could think of that as inducing a vector field on Rn. So at every location C, I get an associated direction given by this vector. And I want to flow along that vector field. So let C, mapping R to Rn, be any trajectory or integral curve of the ODE given by C prime is equal to R C. So again, I have a vector field in n-dimensional Euclidean space, and I'm choosing to start somewhere, and then I'm just going to follow this vector field around under an ODE flow. And given this, I'm going to define a scalar conservation law for some function theta. It's going to move at speed lambda evaluated at this trajectory, xi. Now I'm going to plug theta in there, and that will give me my function a. So it's just helpful to track, where our different quantities are living. So theta is a scalar variable, so it's taking values in r, which I'm then using essentially as a time coordinate in this particular integral curve. So I'm plugging that real value into xi, which is going to give me a location in n-dimensional space. And then at that location, I'm evaluating the corresponding eigenvalue that I've been thinking about. So remember that lambda is always a function of Rn, so I can't just plug theta into it directly. I need this intermediate expression, xi. Okay, so this is a bit unmotivated so far. I've said, let's think about some integral curve and then an associated scalar conservation law. But we can bring this back to the hyperbolic conservation law that we started from. So consider now capital theta, which will be defined to be the composition of this trajectory with little theta. So again, I'm kind of thinking of little theta as determining some parameter, and then I'm studying the location of along this integral curve at the value of that parameter. And I claim that this capital theta, which is now going to be vector valued, is going to satisfy our conservation law. The original, more complicated hyperbolic system. Let me check this. So if I compute the time derivative of this expression, capital theta, I'm going to get through the chain rule, on the one hand, xi prime composed with little theta, and then I'll have the time derivative of little theta. And I can simplify both these expressions. So on the one hand, this xi prime, by construction, is always going to be a right eigenvector. So this is going to be R of xi composed with theta. And on the other hand, I have a scalar conservation law for little theta. So solving for dt theta and just carrying this expression over, I'm going to get here lambda of xi composed with theta times the spatial derivative of theta. And I can keep simplifying because each of these capital Xi composed with theta is just capital theta by definition. And an eigenvalue times an eigenvector is the same as a matrix acting on that eigenvector. So this is identical to minus A of capital theta acting on the right eigenvector. And finally, I can recognize this expression. Well, kind of coming back, this right eigenvector, as I wrote here, is also equivalently Xi prime of theta. So this expression is what I would get if I differentiate capital theta with respect to x through the chain rule. This is the Xi prime factor, and there's my derivative of theta. So this thing is also partial x of the vector capital theta. And I've now expressed everything purely in terms of capital theta. So bringing things back to the left side, I have this vector valued equation. And that's exactly the system, the hyperbolic system of conservation laws that I was interested in thinking about. So one way to put this is that we've identified that that system has living inside it certain special solutions that solve scalar conservation laws. And it has families of these solutions associated to each eigenvalue that we're working with. So once again, these special solutions have a name. These are called simple wave solutions to our conservation law. And they're particularly nice. The various identities on this board tell us that a simple wave is varying only in one of the spectral components of the matrix A. The variation in the other eigendirections will be 0 because these derivatives only have expressions in terms of this eigenvector, and they have no components in any of the other eigenspaces. So they're simple in the sense that the manner in which they solve the equation is concentrated exactly in one of the eigendirections. And again, for every eigendirection in this problem, I can associate a family of simple waves. A more general solution of the equation will not have this property. A general solution of this system will have variation in all the eigendirections, but this is a special family that is particularly nice in this sense. And because we can analyze scalar conservation laws very explicitly, let's see, maybe it's gone somewhere, yeah. Because we can analyze scalar conservation laws so explicitly, we can say lots and lots of explicit things about simple wave solutions. We can use them to construct examples of certain behaviors in the more general system, including shock formation. So this particular simple wave can form a shock if it's genuinely nonlinear. Here we have an expression for the characteristic speed of the corresponding underlying scalar conservation law. So big theta forming a shock, first of all, is equivalent to little theta forming a shock, the solution of that scalar conservation law. And that will be possible, we're led to believe, when this function is genuinely nonlinear, when the derivative of this with respect to theta is non-zero. So if, in short, if lambda composed with capital Xi prime is not equal to 0. So let me apply the chain rule to this to get a better feel for what that means. And again, it helps to think, where are these expressions living? So lambda is a function from Rn to R. So if I want to chain rule it, I'm going to get a gradient of lambda. And then Xi, on the other hand, is a function from R to Rn. So its derivative will be a vector valued quantity. And of course, we know what that vector valued quantity is from this expression. So if I expand this out, I'm going to have the condition that 0 should not be equal to the gradient of lambda dotted against Xi prime, which is the right eigenvector. So this is the incarnation of the notion of genuine nonlinearity in the context of a system of conservation laws. And it's the condition that will allow you to spontaneously form singularities from smooth data. And just a bit of interpretation, what we're saying, so lambda itself, as I mentioned, is a function of the state variable. So it's a function of R, a function on Rn. And here I want that function to vary non-trivially when I move in the direction given by its own right eigenvector. So lambda is associated to a right eigenvector. I want to say that if I vary the value of psi, the hidden argument here, in the direction of that right eigenvector, lambda should change in a non-trivial way. And that's exactly what's going to tell you that when you study the propagation of some disturbance in that eigendirection, the speed given by lambda is going to change. And when you have that differential speed, you have the potential for crossing characteristics, which can then give you the spontaneous formation of a shock. So this has been carried out in an abstract setting for a general hyperbolic system of conservation laws. Let me now examine this condition in the context of Euler. And again, I will pass over the calculations, but we need to know, do the characteristic speeds, these lambdas that we calculated for Euler, satisfy this genuine nonlinearity condition? And the answer is mixed. So for Euler, the first two characteristic speeds that I mentioned, the first two lambdas, u plus or minus the sound speed, these are genuinely nonlinear. So they are very liable to form shocks. On the other hand, the middle speed, u, can be shown to not be genuinely nonlinear. So it's what's called linearly degenerate. So this quantity is given by 0 in the case of the central characteristic speed of u, which is just transport along u itself. So physically, this is roughly telling you that the entropic component of gas dynamics does not tend to form shocks. It's just transported with the flow, and it, again, does not tend to spontaneously develop any new singularities, but the components of the gas dynamics that are propagating with the speed of sound are very liable to form shocks. And so it's these eigenvalues that kind of lead to familiar generation of discontinuities and such in gas dynamics. And so it's these ones that we're going to focus on. I guess I should be moving the boards. Oh well. Okay, so I'm going to focus on one of these genuinely nonlinear characteristic speeds, and it doesn't matter which one I choose. I'm going to choose the leftmost one. So I'm going to be thinking about first off a simple wave solution of the Euler equations associated to this eigenvalue, associated to essentially the propagation of sound moving leftward. And again, the choice of sign u minus c or u plus c is immaterial. It just allows me to keep track of the ordering at certain locations in the argument. So this is the leftmost or slowest characteristic speed in the Euler equations. And I've selected it because, as I mentioned, a computation can show that this is genuinely nonlinear. Actually, one thing I should briefly mention is that so whether or not you are genuinely nonlinear depends on the equation of state that you happen to be working with. It depends on that function that relates the pressure to the other state variables. Because remember, C is given by a certain derivative of the pressure. So there is one kind of special equation of state, which is independent of rho, and therefore, let's see, is that right? Yeah, and therefore has a linearly degenerate associated speed. But you have to be in that special equation of state in order for the whole analysis to fail. And for any other equation of state, things are going to be fine. And that equation of state is not one that is typically found for regular gases moving around, like air, for example. I'm not an expert in the physical literature. I don't exactly know if there are gases that are known to have anything approaching that special equation of state called the Chaplegan gas. It does arise in certain cosmological theories. But so we'll ignore that kind of special weird gas, and we'll work with anything else, which includes real world gases like the ones present in this lecture hall. Then we get that genuine nonlinearity. And as a result, we know that shocks can spontaneously form, in fact, often would spontaneously form in simple waves that are associated to lambda. Because these simple waves are solving, essentially are solving a scalar conservation law whose speed is given by lambda, and therefore it's easy to cook up examples of initial conditions that will have crossing characteristics and therefore lead to shock development. But as I mentioned, in some sense, that's just the beginning of a general theory of shock formation in the system, because these simple waves are very special solutions we've cooked up to be particularly analyzable. They're kind of special, particularly integrable examples of solutions. I would like to understand the sort of viability and the nature of shock formation for more general solutions of the equation than just these special examples that we've cooked up. And so the way I want to frame things is, let's say, we're running an experiment in the lab with some gas, and we've cooked things up so that we're at least very close to being such a simple wave. So we've arranged our initial condition so we look like a simple wave kind of to a casual observer. Well, of course, any experimental setup is going to have some errors associated to it. And so there's no way that I know of to ensure that your initial condition will exactly be that simple wave. So given that I can't perfectly select such a solution, do I know that my experimental setup will still exhibit the same kind of behavior? So to put it a different way, is the development of shocks in the simple wave stable to arbitrary perturbations of the initial condition? That's the kind of thing that would be required to observe shocks in the real world, again, because we should never expect to be able to perfectly contrive one of these special solutions. So the kind of the broad motivating question I want to think about here is the stability of the shock formation near, but not exactly on top of a simple wave. So is the process that we would refer to as shock formation stable to small perturbations around a simple wave? And as I mentioned, this is a mathematical question, but it's of relevance to our physical understanding of the gas, because if the answer were no, then maybe it would be difficult to observe shocks happening in the real world. And the answer is yes. So this is work of myself with John Anderson, who will be speaking next week in the GR section of our semester, and then Sanchit Chaturvedi, and myself. And I should have said at the beginning that, in fact, my entire lecture series is based on a couple of joint works with John Anderson and Sanchit Chaturvedi. So in short, the answer to the question is yes, with some minor caveats. So let me put it like this. So shock formation is stable near a genuinely nonlinear and extremal simple wave. So by extremal, so we've already discussed the genuine nonlinearity condition. By extremal, I mean that the associated eigenvalue, lambda, is either the smallest or the largest of the set of eigenvectors. So I list out my eigenvectors in order, and if I happen to be working with one of the endpoints, then unconditionally I can say that if I have a simple wave associated to a genuinely nonlinear eigenvalue at one of these endpoints, then that forms a shock. Then if I perturb it slightly, I'll still form a shock nearby in space-time. So it turns out that although it's not obvious from the discussion so far, this condition of extremality is massively convenient in the analysis of the system. So studying a fastest characteristic or a slowest characteristic has numerous technical advantages compared to studying a characteristic that is in between other characteristic speeds. Now, we can still say things about these, a characteristic of intermediate speed. So if lambda is intermediate, the same holds for simple waves that satisfy a very, very mild form of non-degeneracy, which basically means that they can't simultaneously develop a shock over a very large interval of state variable values. And I'll draw a picture to represent that in a moment. And we're actually not sure whether if you have an extremely degenerate simple wave of intermediate speed, we're not sure whether one can construct examples of unstable shock formation or not. So I'll write that as an open question for the crowd here.
Sorry, if your speed is intermediate, you form a shock along its characteristics. Is that the only genuinely nonlinear speed, or are you allowing other speeds to also be genuinely nonlinear?
Yeah, I would. So what's required here is only that the particular eigenvalue that you're studying is genuinely nonlinear. The genuine nonlinearity of the other eigenvalues sort of doesn't play a role in the statement. Now, what you might be thinking is that, okay, well then you could form a shock in one of the other characteristics as well. Yeah, yeah, exactly. So here I should say what I have in mind. So that gets at the question of sort of what near means, right? So here, let me mean close in a C1 sense. So I'm close to a simple wave in a C1 sense. What that means is that the variation of my data in the other characteristic directions is going to be small in C1, and therefore it won't have time to form a shock before you develop a shock in the kind of principal direction that you're studying, that your simple wave is shocking in. So if you're close in a C1 sense, then you would avoid the issue you're referring to. If you were only close in C0, then of course there'd be nothing preventing spontaneous shocks all over the place instantaneously. Does that kind of address things? Yeah.
Can you say a little bit also on the restrictions on the state profiles that allow you to form a shock?
Yeah. In other words, elaborate on the non-degeneracy that I mentioned there. Yeah, certainly. So first off, let me also elaborate slightly on what the conclusion is here. So shock formation being stable means that psi forms a first shock near where the background simple wave theta does in space-time. So if I perturb the data of theta, I could shift the location and the time of that first singularity a little bit, but I won't spontaneously develop a new shock in a completely different place. And I also won't be able to prevent the formation of a shock near that near the kind of breakdown location of theta. So that's what I mean in a bit more precision. And so what do I mean by, so for intermediate speeds, what does the non-degenerate mean here? Non-degenerate. So let me just draw, it's easier to draw the condition than to state it. So I'll actually elaborate on the reason for this in a moment, but the point is that at the moment when you're first forming a shock, your solution is going to undergo a gradient catastrophe, meaning somewhere its gradient is going to tend to infinity. And there are various profiles that fall under that condition. So here's an example of such a profile. This is about to form a shock, basically right there where it forms an infinite slope. If I evolve this forward for any positive amount of time, I'll develop a discontinuity if I'm solving it in an entropy sense. So this is one example. But there are more extreme degenerate examples where not only do I form an infinite slope at a single value, but I could cook things up in such a way that an entire interval of values simultaneously become vertical. So this is one example, but another more severe case would be that I have an entire vertical interval of infinite slopes here. And non-degeneracy here means that the kind of height that I've drawn here, which represents a length of intervals within state space, that should be small. So the non-degeneracy that I have in mind allows, at the moment of a breakdown of your C1 solution, allows your solution to have jumps, but the jumps have to be sufficiently small. And I would say probably graphically this is not representing a small jump. This is representing rather a large jump. So so maybe a better way to put it would be something intermediate where I have a little bit of a vertical interval here that isn't too large. And in kind of a generic case, as I'll argue in a little bit, so for typical initial conditions, let's say, you shouldn't actually expect to see any full interval of singularity at the moment of shock formation. You should just expect to see a single location that has an infinite slope. So sort of for typical data, you're going to be in this non-degenerate condition or situation, but it's possible to cook up data where you have a very large jump at the moment of singularity formation. And those are the ones that that we're not sure about in terms of the stability of the corresponding singularity. And yeah, so somehow if you were trying to cook up an example of data like this that is unstable in the sense, we suspect the way in which it could be unstable is that this large singularity in one of the eigenvalues sort of manages to transfer to a singularity in one of the other eigenvalues shortly around the location of shock formation here when you perturb the data slightly. But we don't actually know that that can happen, and we don't know how to rule it out. You can kind of write down some formal equations that might suggest that there's potential instability in this scenario, but again, we don't have a concrete proof one way or another. So all of this kind of qualification holds for intermediate speed shocks. Let me point out that for the Euler equations, there are no intermediate speed shocks, because for the Euler equations, the genuinely nonlinear characteristics are the extremal characteristics, those traveling at u plus c and u minus c, with the third characteristic in the middle. So for Euler specifically, this is not an issue. You're always in the extremal case, and therefore you always know that if you have a simple wave that's forming a shock in one of those extremal characteristics, that process is going to be stable to arbitrary C1 perturbations. So let me say a word about how one goes about tackling something like this. So this is a very standard idea in hyperbolic theory. We're going to introduce a kind of funny looking coordinate to the problem. So we're going to let V solve what's called the Eikenel equation associated to the shocking eigenvalue lambda. So I'm going to take my solution, C, whatever it is, I'll plug it into the eigenvalue that I'm studying. That'll just give me a function here of space-time, and I'll just use that in a linear advection equation to drive around the values of some auxiliary variable v that I've introduced. And the idea is that this is much like in the method of characteristics. The values of v are conserved along the characteristic curves of our solution, moving with the shocking eigenvalue speed. So v is basically tracking the location of those characteristic curves. And in particular, this will tell you that v is actually going to let's say, become singular in exactly the same way that psi will become singular, because it's getting dragged along by exactly the fluid velocity that is going to be causing a shock to form. So v is basically getting dragged along by psi to form a singularity in exactly the same way. So v forms the same sort of singularity as psi. And that might initially look implausible because we're used to looking at a linear equation and thinking that everything should be fine. But the point is that the advection here is going to develop an infinite slope at a certain location, and that's going to cause v to get dragged along into a similar behavior. And the key observation is that one can actually sort of change your viewpoint completely and think about v as a coordinate and express the equations of motion in terms of this coordinate rather than in terms of space. So one can use time and the solution of this Eikenel equation as a new coordinate system. And again, this is a familiar idea from the context of scalar conservation laws, where well, the values of v would essentially coincide with certain values of the solution itself. And in that case, you would find that the solution is just a constant function of v, independent of time. In the system setting, the solution psi will not be constant in time as a function of v. It will vary with time as well, but it turns out it will vary in a smooth fashion. So the key observation is that psi remains smooth as a function of these new coordinates. And that sounds strange because we know that in the spatial coordinate system, the solution is developing various, say, infinite slopes, certainly, maybe even discontinuities. But these are not contradictions because v itself is also becoming relatively singular in the spatial coordinate system. So if you can prove this, if you can prove that psi remains smooth as a function of t and v, then the analysis just boils down to understanding how v relates to the original spatial coordinate system. If you can show that it is becoming singular in a particular way, in a stable way, then the same result will follow for psi. And the advantage is that V is a scalar satisfying a scalar equation. So its analysis is much more straightforward than the analysis of the full system. So the goal would be, first of all, to show this fact that psi is remaining smooth in this new coordinate system, and then to develop a good understanding for the behavior of V when you try to convert back to the original setting. And so let's suppose that one can prove this. And of course, there's a lot of work that goes into proving something like this. The idea, though, is just to using this equation to rewrite your hyperbolic conservation law in these new coordinate systems, basically using the chain rule. And then you study those new equations in that new coordinate system, and you try to show that those new equations have basically removed all their kind of singularity forming tendencies, that you have factored that out by introducing this new coordinate system, and that those new equations are going to remain nicely behaved as you evolve forward in time. And then, as I mentioned, then you want to study the conversion between V and the original function x. So a gradient catastrophe in psi, by which I mean psi developing an infinite slope somewhere, is then going to be equivalent to the change of variables between V and x becoming singular. And a nice way to put that is that the derivative of of x with respect to V will go to 0 somewhere. So if I think about what that means, let's just look at one of these pictures. On kind of in a caricature on the vertical axis, I can think of the vertical axis is representing this iconal function V. This is not exactly true, but morally it's true. And the horizontal axis is depicting x. So at a location here, I'm varying the value of V, and yet my x coordinate is hardly changing. So the infinite slope that I see in this orientation of the graph can be kind of inversely expressed as the vanishing variation of x with respect to V. Equivalently, that would be the infinite variation of V when I try to vary x. But this is a much more amenable condition to try to prove. And again, this is just telling you that the change of coordinates between V and x is becoming singular at a certain location, which reflects shock formation in your gas. And it turns out that this is not such a difficult thing to prove once you set up all the equations properly, because you can actually write an equation satisfied by this quantity, this kind of crucial quantity, which is basically the Jacobian in the change of variables from V to x. So one can write an evolution equation for this quantity and one can show that it must fall to 0 in a stable fashion. So your simple wave solution will be causing this quantity to spontaneously reach 0 at the location where the simple wave becomes singular. And once you re-express all your equations in this new coordinate system, you'll find that this Jacobian quantity is going to satisfy a relatively nice equation that will be stable to perturbations, and therefore this value will likewise be driven to 0 at a nearby location if you perturb all the data slightly. You can't avoid that through any small perturbation. So this is the kind of thing that will force your more general perturbed solution of your problem to develop a singularity close to the location where the simple wave developed a singularity. And I wanted to say one word about why let's see, extremal wave speeds and intermediate wave speeds might differ in this analysis. You know, why is it that we should have more difficulty treating the intermediate case? And the difficulty comes in understanding the components of psi in the kind of non-shocking directions. In other words, the components of psi in the eigenspaces that correspond to the other eigenvalues not equal to lambda, not equal to the one that we're studying. So need to control psi in the non-shocking directions. So you need to write equations for the components of psi in those other eigenspaces, and then you need to show that because they start from small data, they're going to stay small. And the key difficulty comes in the expression for these equations. So these equations, let's see, let me put it like this. Near the singularity, these equations are roughly given by the following. They'll roughly be given by lambda tilde minus lambda times partial v of, I guess I'll call it psi, equal to some stuff. So here lambda tilde is any other eigenvalue. It's an eigenvalue corresponding to one of the other non-shocking components, and lambda is the shocking eigenvalue that we're basing our whole analysis around. And because we have genuine nonlinearity, this difference is non-zero, so at least this is kind of a non-singular differential operator. But you can start to see where intermediate versus extremal speed might matter. So if I'm at an extremal speed, so if lambda is extremal, then for all the choices of lambda tilde, this will have a consistent sign. For example, if lambda is the slowest characteristic speed, like I selected, then the lambda tildes will always be greater than them. And so this will always be a positive number in that case. And inversely, if I were studying the fastest characteristic speed. When these all have a consistent sign, this just looks like now an evolution equation in V, all oriented in the same direction. So it's a system of evolution equations, but they're all pointing in the same direction. So I can actually kind of change my perspective again and think of V as a time coordinate, just in the context of ODEs. I have a system of ODEs, maybe you give me some data, and then I try to solve them, and I'm solving all these ODEs forward in V in the extremal case. But in the intermediate case, some of the components of this system will have a positive number here, and some of the components will have a negative number here. So instead, it's like an ODE where some components are moving in one direction and some of the components are moving in the other direction. So to kind of, draw things out intuitively, when I'm thinking about the evolution of these non-shocking components, I basically get different pictures depending on the classification of the shocking eigenvalue. So in the extremal case, I can think of my system as though I have some pieces of data here, and then I have several components, but all of them are evolving in this direction. So the different lines here represent different scalar components of this system of equations, and they're all oriented in the same direction. I give you some small data here, and then I try to solve them forward in V. But in the intermediate case, we're oriented differently depending on the non-shocking eigenvalue under consideration. So really, it looks like I have maybe a few components going in this direction, and then I have a few components going in another direction, potentially. And this is a bit rough, but the general takeaway I want to leave you with is that I could think of this as an initial value problem for an ODE in the extremal case, but this is more like a boundary value problem for the intermediate case, where I have data on two sides and I'm trying to solve through the middle, whereas here I'm given data on just one side and I try to evolve forward. So in a very rough sense, again, this is analogous to an initial value problem. And this is analogous to a boundary value problem. If I have an initial value problem with small data and the right-hand side is small, then I could use the Grunwald inequality, for example, to prove that my solution is going to stay small. And that gives me the control that I need. But if I have a boundary value problem and I have small data and small right-hand side, it's not enough to guarantee smallness of the solution. You know, you could have you could be sort of in a resonant situation where there's some eigenvalue corresponding to your boundary value problem that leads to large solutions in the interior, even if you have small data on each side. I mean, just think about a second order equation where sine of x solves the harmonic oscillator, but it vanishes at two endpoints. That's kind of an extreme case, but the point is that in general, for boundary value problems, you're not guaranteed to be able to get smallness from smallness of the data. It depends on the width of the boundary value problem. And that width ends up being related to the size of the potential discontinuity that you are forming in your simple wave. So if you have too large of a discontinuity in your simple wave, you might have potential resonances in the associated boundary value problem, which could lead to instabilities in the equation. So, you know, this is a very hand-wavy perspective, but I hope it conveys some idea of the technical challenges that arise in the intermediate case that don't arise when you're studying the extremal setting. And the way to circumvent this, if you have sufficient non-degeneracy like this, is to argue that although you do have a boundary value problem, it's over morally a small window, and therefore you can still argue that you can propagate smallness from the boundary. So maybe I'll record for enterprising folks out there. I should keep. This question that we're definitely intrigued by, which would be the potential construction or realization of this instability that basically we can't rule out. So an open question would be, can one construct very degenerate it would have to be very degenerate, unstable intermediate shock formation. And here, you know, you would sort of have the freedom to design a hyperbolic conservation law of your choice, provided it's genuinely nonlinear in one of the intermediate speeds. And you could try to write down a simple wave that has a very large jump at its first singularity, so that it's very degenerate. And then you could try to select everything about the problem just right so that you manage to produce an instability like this. I don't know whether this is possible, but I should like to see an answer.
Yeah, instability can mean many things, right? It can mean singularity in another characteristic speed.
Yes.
Removing the singularity altogether.
Yes. Yes. Yeah, exactly. Yeah, because the stability statement tells you lots about the problem, and violating any part of that stability statement would be enough for my interest. And I think, like you just mentioned, it seems to me that you wouldn't be able to entirely remove singularity formation, but rather maybe there's a way of sort of transferring this shock formation into another characteristic in a way that doesn't happen in the scenario described up there.
So this pertains to the non-shocking direction, but in the shocking direction, what does the equation? It's not this equation, but what's the key equation?
Yeah. Yeah. Thanks for the question. Yeah. So exactly. So just to restate the question, so these equations govern the non-shocking directions. And of course, in some sense, the shocking one is the one that we're most interested in. So what's going on there? So one can show that then in these new coordinates, in the TV coordinate system, let's see, let me write it here. For the shocking direction, you're basically going to get the time derivative of C. And again, this should really be the coordinate of C in a shocking direction being given by some fairly well-behaved things. This looks a little weird because you should be able to write down a similar equation in the original coordinates and you wouldn't have any kind of nice behavior here. But one of the differences is that this partial derivative d tau is going to be different when you're working in this new in this new coordinate system. Or excuse me, dt. When I'm working in the new coordinate system, t and v, this partial derivative should represent t with v held constant, which will in general differ a little bit from dt with x held constant. And the idea is that I can express this in terms of various other derivatives of my solution. And actually, I'll find that the other expressions are going to become small close to the singularity. So this ends up being something that can be integrated quite simply close to the singularity. So the kind of setup of analysis to carry out this whole program ends up being you first show that you can control the non-shocking directions. That's what allows you to then say that the right-hand side here is relatively benign, because of course it will involve contributions from all the components of your equation. Once you have that, then you can get kind of a nice right-hand side here, which will allow you to conclude that the shocking direction is relatively well behaved in this new coordinate system. And then you can control higher derivatives of all these expressions with respect to these different coordinates as well.
Sorry.
Yeah.
One, the stability in this region, it's not C1 anymore, right? Is it an infinity? Because if you have a discontinuity,
yes, you mean yeah, the sense of stability here, yeah, is not in C1 and X. Yeah.
And so here's the other question, which might be too technical. So all of your analysis is in TV coordinates.
Mm-hmm.
In the extremal case, then you can prove, the way I understand your paper, is that the TNX and the TNP coordinates are in bijection with each other. And so you can translate everything from TNV back to TNX through the change of variables and recover the gradient flow with this dEx equals 0. And like,
Yeah, I guess I would qualify it by saying right at the moment where things break down, you don't necessarily preserve a bijection, but up to that point, it's fine.
When your data is this cubic thing,
Mhm.
I think you do get a homeomorphism.
Yes.
It's no longer a diffusion.
Yeah, that's
It
right.
is in bijection.
Yes, in the
Actually,
cubic case, it will be.
yes,
Yeah,
the characteristics don't cross.
right.
That's the gradient flow.
True.
But
Yeah.
the question is now, how do you relate this change of variables in this unstable case, in this intermediate case? Because it looks like you're going to have a massive loss of one-to-oneness.
Yeah, like in this situation.
Exactly.
Yeah, where you have this
So
giant
how
change.
do you recover anything?
So this is in the more non-degenerate case where you shock along and you form an entire discontinuity at the first singular location. So you can still recover various statements like, well, you recover statements of closeness of the form described here, that if you look at the location where your solution is first becoming singular in space-time, that location will be close in space and time to this location. But there are some important subtleties because, for example, if I slightly perturb a scenario like this, it's possible for a slight, in fact, it's probable that a slight perturbation will itself not first shock along an entire interval, because it might first shock at one of these intermediate values before the other values become singular, if I adjust things slightly. So the value of V and the value of psi, where I'm developing a shock, can change dramatically in this degenerate situation at the location of first shock. There are still some notions of stability one can write down in that setting, but yeah, it gets a bit hairy to express concisely. I should say also, I'm not going to get into this, but one can express some of these questions in terms of the maximal development, the geometry of the maximal development near singularity formation. And there you can say that in a certain sense, the boundary of the maximal development is not changing very much in kind of like a Hausdorff sense in space-time relative to the original boundary. But that's kind of, maybe beyond what I want to say right here. Yeah. Okay. So Leo was just mentioning some of the specific details that pertain in particular to this case, where you have a certain very nice and very non-degenerate form of the first singularity. And so I want to tease out a little bit more in detail what I should expect a typical first singularity in Euler to look like. Not necessarily any possible first singularity that you could cook up, but one that you would see in practice, because most of the time it will have a certain nice structure. So I want to say that a typical shocking solution of Euler is not going to look like this, but it's going to look more like that. So So I want to be a bit more precise about what I should usually expect to see. And so I want to give you a detailed description of the structure of this new singularity that is being born when we're in kind of a generic case. So this picture already shows that, you know, I can't give you a single form that will always describe the detailed behavior of your solution close to its first singularity, because I might look like this, or it might look like that, and these have rather different behaviors. But I want to argue that this is not something that you should typically expect to see. Rather, one would typically expect a first singularity to look like this, where I am first developing an infinite slope at a single location along this graph and in kind of a non-degenerate way. So how can I get a feel for what this should look like? So let's start with a scalar equation. So returning to this example of some scalar conservation law. Now remember that this could actually represent implicitly the behavior of a simple wave solution for the more general problem, because then I could just take A to be the composition of lambda with that trajectory xi, and I would have an example of a solution to the full system. So I want to zoom in on the behavior of theta near its first gradient catastrophe. And there's a bit of normalization that I can do to simplify my life, to simplify my analysis. So through a Galilean change of coordinates, I can arrange the following. I can arrange this first gradient catastrophe to occur at t equals 0 and x equals 0. This is a simple matter of shifting my time coordinate and shifting my spatial coordinate. And I can also arrange that it happens with 0 instantaneous speed, by which I mean that A of theta of 0, 0 is equal to 0. And this might not look like something that I can automatically arrange because, you know, how can I choose the function A? But the idea is that I could shift into a coordinate frame that is moving with the speed of my characteristic at the gradient catastrophe. And after I shift into that co-moving frame, the relative speed will become 0 at that single point. So this is also something that I'm free to do through one of these Galilean change of coordinates where I allow myself to shift into a moving frame. And this helps simplify my understanding of the problem a little bit. I'm also free to subtract a constant value from theta so that I can arrange this value in the interior to be 0. That's basically because the values of theta are sort of arbitrary. I can always add or subtract constants, as I mentioned, and I won't really change the fundamental behavior. So I can also set this to be equal to 0, basically through a change in my, my state space. So all of this has the effect of taking my first singularity and shifting it to the origin in space-time, saying that theta will vanish at that location and that the corresponding speed of my conservation law vanishes at that location as well. That will mean that the origin is actually a stationary point in the evolution of the equation. So let me draw a picture for what that can look like. I'll do it right here. So I'll draw several time slices of the solution. leading up to the first gradient catastrophe. So the first time slice might represent the initial condition, which, by the way, has been shifted backward in time to some negative time. So I'm prescribing data at a negative time, and then my solution is going to become singular at t equals 0, just for convenience. So maybe my initial condition is here, and it starts off nice and smooth. And this is kind of a classical picture of data for the Burger's equation, for example, that is going to develop a shock in finite time. So this is at t naught, which is less than 0. And here I'm plotting x on the horizontal axis and the value of theta on the vertical axis. And now I want to imagine evolving forward a little bit. And remember that, so I'm passing through 0 at x equals 0. And a, the speed of my characteristic is vanishing at that location because I've shifted to a co-moving frame. So this point will actually be stationary. So my curves will all have to pass through the origin, even at future times. So at a slightly later time, maybe the two lobes of my solution are going to move toward each other through that genuine nonlinearity, which causes them to move at differential speeds. And I'll get something like this. So this is at some time t that is between my initial time and 0. And then finally, let me draw the catastrophe that is developing. We can already kind of see it hinted here. The slope at the origin is becoming steeper and steeper. And at some finite time, if I can draw it properly, at t equals 0, technically, I'll have a negative infinite slope at the origin because of all the changes of coordinates that I've contrived here. So this is basically using the gauge freedom of my problem to simplify the picture, so I can analyze it in detail. And I want to get a detailed understanding for what this profile could look like as I come in and approach that, that singular time. So that red curve over there corresponds quite a bit to this picture here. So I'll leave that up. So in any case, near x equals 0, theta is going to be close to 0 because we've chosen it to always pass through that location. So to get a kind of first order understanding of the behavior of our equation, it makes sense to linearize that advection A around 0. So we should expect the A of theta is going to roughly look like A prime of 0 times theta. Again, zooming in close to that first singular moment. And we're working under the hypothesis of genuine nonlinearity. So there's that expression again that popped up earlier. This should be non-zero, this derivative of A. That's what's allowing characteristics to have different speeds. And it sort of makes no difference which sign I choose. Let's say that it's positive, because that's consistent with the drawings that I've made here. I would have to flip my vertical axis if I wanted to draw this picture with negative values of A. So let me not do that. So I'll arbitrarily consider the situation where A prime is positive. And now our equation at leading order is going to look like a scaled version of the Burger's equation. So I've replaced my full nonlinearity by its linearization around the origin. And I'm saying that sort of at leading order, this is the equation that we really have on our hands. So in fact, close to that first singularity, you can approximate the behavior of the equation by some scaling of Burger's. Now, what does Burger's look like in this scenario? So I can basically imagine that I've completely simplified my problem, and I'm just trying to understand the generic behavior of a solution to Berger's equation as it undergoes a gradient catastrophe. And what you'll find is that, again, in a generic case, there's a sort of a universal first gradient catastrophe that one observes in Berger's. So one can carry out this calculation explicitly using the method of characteristics. And for the sake of time, I'm going to pass over the details of that calculation. But the key point is that if we consider the spatial inverse of U, one can actually write down a very simple evolution equation for this spatial inverse under Berger's. And that will allow you to basically explicitly write formulas for this spatial inverse. So what you're going to find, let me call this spatial inverse Z. What you'll find is that dt of Z, say it's a function of t and y representing the kind of inverse variable corresponding to U. You'll find that dt of Z is going to be equal to a prime of 0 times y. That's actually an equality for Berger's. And of course, this is practically not a PDE. This is really just an ODE that we can explicitly integrate in time. And we'll conclude that Z of t and y is equal to its value at 0 plus a prime of 0 times t times y. And then the question just becomes, what can the value at 0 look like? So because Z is representing the spatial inverse of our function, what we're basically doing is we're taking this picture and we're sort of rotating it by 90 degrees to think about this as x expressed as a function of Z, which, by the way, is very similar to the transition between x and the iconal coordinate v that we used in the hyperbolic analysis. And we're trying to understand what this profile should look like. And we have various constraints on it. So at t equals 0, we know that we need to have an infinite slope in this graph, which means the inverse should have vanishing slope at the origin. That's because of that gradient catastrophe. We also know that we arranged things so that for y equals 0, the inverse value is also equal to 0. So we know that z naught should vanish. And because of that gradient catastrophe, z naught prime should vanish. What about the second derivative of z naught? If I had a non-zero second derivative for z naught, it would look like a little bit of a parabola here. And I know that my graph can't look like that because up to this first gradient catastrophe, I still have a bijection. So I can't have a multi-valued graph here, and therefore I can't have any second derivative at that moment of shock formation, because that would actually imply that I had formed a shock earlier than I'm telling you. So in addition, the second derivative of z naught must vanish. Now, thankfully, there's nothing that tells me that the third derivative of z naught vanishes. So I'm basically developing a Taylor series for z. I've written down a bunch of nice conditions, and this is where I get to stop. And I get to say that in general, there's nothing preventing a third derivative here, which is actually roughly what you see in this picture. If I rotate my perspective 90 degrees, I see the graph of a cubic function here to leading order. So the conclusion that I want to draw here, and that's where I'll leave things, is that generically, to leading order, at the first gradient catastrophe, our solution theta of t and x is going to look asymptotically close to the origin, like a special profile, theta bar, which is going to satisfy, through this inverse relationship, a cubic equation. So I'll have a linear term in my equation from it coming from the time evolution. And then I'll have some cubic term, which one can compute to have a negative sign. And the inverse cubic function satisfying this equation will basically give you the germ of a generic solution to our scalar conservation law at the moment when it first develops a singularity. I'm emphasizing the word generic because, in principle, if you set up your data properly, you might have a vanishing third component here as well, in which case there would be some higher part of a Taylor series to be satisfied. But this is non-generic in the sense that if I perturb initial data of that form, I should generally expect to produce a non-zero cubic term in my Taylor series, and I'll find myself back in this scenario. So this is kind of the only stable, simple germ that would describe shock formation in a scalar conservation law. And we'll see that this shows up in a more general system as well. So I'm out of time. I'll end there for now. Thanks, everybody.
Thank you.